Okay, good afternoon. Welcome to this webinar on decision support tools for regional climate adaptation. My name is Raul Glasbach. I work with the KWR Water Research Institute. Before we get into the webinar, just a few house rules. So as you noticed, we are recording the webinar. This is for purposes of communication. Also, we kindly request that you keep your camera off and also your microphone muted unless you would like to pose a question. Then we invite you to turn your camera on and to also unmute yourself. But you can also use the chat functionality to post questions throughout the webinar. And towards the end of the webinar, we'll have time dedicated to respond to those questions. And also lastly, we have a survey which we'll share a link towards the end of the webinar, which we'd like to use to gather more of your insights and ideas on the decision support tools which have been presented. Before I pass the floor on to the speakers for today, we'd also like to invite all of you who are participating to share in the chat your name, your organization, your position within the organization, and your country of origin, so that we can just get a sense of who is joining us today in this webinar. With that, I'd like to pass on the floor to Dionysius, who will take on the responsibility of presentations.
Thank you so much, Raul. It's a great pleasure to see so many people attending our webinar. I think this is a great success for our project. Just a few words before we start. IMPETUS is a Horizon project with the ambition to aid in accelerating Europe's climate adaptation strategy through multidisciplinary teams that co-create with policymakers, businesses, and communities at the local and regional levels. In IMPETUS, we have 7 demo sites where we test adaptation solutions that reside in different biogeographical regions. One of them is at the heart of today's webinar. Oops, sorry, I misclicked. And is the East Attica region. East Attica is a sub-regional unit of the province of Attica, and is in very close proximity to the Greek capital, Athens. East Attica has a population of around 500,000 people. It has large agricultural and natural areas. Some of them are degrading rapidly due to deforestation, and also is home to the Athens International Airport, 2 major ports, and large industrial activities. Currently, unfortunately, we have been observing drought conditions for at least 2 years, and the water reserves of the external supply system have been greatly reduced. You can see the evidence from the lady that makes the reportage inside the reservoir. At the same time, we also have severe wildfires in the region, and while there are multiple reasons for them, like arson or the unprepared state, unfortunately, the sustained high temperatures we experience in summer and the prolonged dry conditions increase the risk. So there is major concern in the region for the future, and we would like to know what is ahead of us in order to prepare and anticipate the climate change. However, nobody can predict the future, so we can only speculate by exploring what are called the shared economic pathways, or SSPs, which are a set of narratives that describe future development pathways for humanity as a whole. These narratives turn into quantitative projections, plant use, energy use, water use, and other parameters using integrated assessment models that correspond to various radiative forces. The coupling model through comparison phase 6 prioritizes 5 of these SSP scenarios that are coupled with specific climate model experiments, and 3 of which are roughly comparable with the previous phase. So these are the SSP1 with RCP 2.6, SSP2 with RCP 4.5, and SSP5 with RCP 8.5. Each of these narratives produces a vastly different set of future conditions for climate, because SSP1 is the pathway for sustainability of humanity as a whole in the future. SSP2 is the middle of the road scenario, where we continue with our current development patterns, and SSP5 is the fossil fuel development, which is the maximum overdrive for consumption of resources, economic growth, etc. So let's explore how do these narratives force the climate in our region. In this graph, you can see an analysis of 24 climate models, 8 for each one of the SSP1, SSP2, and SSP5 narratives, alongside the historical records for mean annual temperature for the region. You can see that in the last 40 years, we have been observing a clear upwards trend in the annual temperature. And in the future, the mean projection shows an increase of around 3 degrees Celsius. Of course, there is great uncertainty from the projections, as you can see with the confidence interval. But unfortunately, the future is warmer. By exploring the total annual precipitation in the region, we can see that even though there is even higher uncertainty and greater variability, again, there is a clear decreasing trend. And lastly, by exploring the standardized precipitation or precipitation and evapotranspiration index, or SPEI, for 48-month periods, we can see also a clear trend of extreme drought conditions in the future. This index has values up to -1.5 for moderate droughts, values up to -2 for severe droughts, and any value that is below -2 denotes extreme conditions. As you can see with the mean projection from the 24 models, drought conditions will be persistent in the future and also much worse than the worst historical event that we had in the region in 1989 to 1993. What about the socioeconomic changes in the region? These are more tricky to calculate, but based on the SSP narratives, we can see that there will be mild to high population change in the region, in contrast with the general Greek population trend that is decreasing due to urbanization. Also, the narratives depict a figure of better economy. Let's hope that this will be true. But unfortunately, this means that the water consumption in the Attica region will at least remain steady for the future or even rise sharply in some of the scenarios. This fact, coupled with the hydrometeorological projections that you just observed, means that the future is riddled with socioeconomic drought. And while we can tackle these issues because we have many options for adaptation, like proposals at the larger scale, for example, desalination plants, new water infrastructure, reoperation of older groundwater wells, etc. This is a very tricky situation. We can also include local adaptation solutions in the region. For example, rainwater harvesting, sewer mining units, controlled environment agriculture, tertiary wastewater treatment and reuse, and other possible interventions. However, it's very, very difficult to choose between them. Our time is limited, our budget is limited also, and we are in dire need of decision support tools in order to foster this whole process. And this is something that's not unique only to the East Attica region, but it's a global problem. And this brings us to the first question that we need to address to you, the audience, in order to gather some feedback about our work. So the first question is if there are institutions in your own region that develop master plans in order to address climate risks. I know that probably this is a trivial question because, okay, probably there will be, but we're interested to see if there are cases where this is not true. You can use now the menti.com website, put this use code that you see in the screen on the prompt text, and then you can vote on this question and every other question that you will see coming up in the webinar. I will leave this question open for around a minute, so everyone has a chance to participate. I see that we have some new attendees, some information about this webinar. We are now to the stage of collecting some feedback, some preliminary feedback. So if you just Got in, just go to the menti.com website, use the passcode you see on the screen, and you will be able to vote in the questions of this webinar. Okay, I think we have had enough time for vote. You can always go back and change things in the menti.com website, or if you didn't have time now to vote, you will have the opportunity later to do so. Let's proceed with the next question. The next question refers to whether there are already decision support tools in your region that are able to generate adaptation pathways to address climate risks. It's very interesting to see that even though most of the regions have regional authorities that are producing master plans and projections for the future and business models, can see that clearly half of these regions do not have any decision support tools, or the audience is not aware of decision support tools that drive this approach. Very interesting. Okay, so this brings us to the next part of the presentation, where we will examine what IMPETUS does with regards to this issue. So IMPETUS steps in, and because there are similar problems common across all European biogeographical regions, but even to a global scale, our project builds decision support tools that foster this approach. Pivotal here is the strategic planning notion of adaptation pathways. Adaptation pathways is a delineation of regional climate adaptation interventions at specific decision time steps in order to tackle climate risks and reduce their impacts. You can see a schematic diagram of what adaptation pathways look like in the figure below. So we have here three different pathways: the blue one, the yellow one, and the green one. Each goes from the baseline regional conditions to the conditions that the region experience in the future at the end of the strategic planning horizon. Each one of these pathways includes a different mix of interventions, and each one has some distinct advantages and disadvantages. For example, the blue pathway may be the most performant, while the green pathway may be the one with the least cost, and the yellow one being the one that has the higher social acceptance. NTUA's work, along with our partners in IMPETUS, our specific work package, is to lead the development of a toolset and a methodology in order to foster climate resilience and adaptation. We have done already some background work with some interesting tools that unfortunately we will not be able to cover today, like the Climate Hotspot Identification Prioritization Service, a comprehensive indicator and metric framework, and some econometric models for climate interventions that are able to assess their cost effectiveness and their hidden risk. But today's special are two tools and a methodology for doing exactly this, delineating adaptation pathways. The two tools are named Risk and Emerging Problems Inference Engine, or REPIE for short, and Dynamic Contingency Response Tool, DCRT. The general methodology to produce adaptation pathways involves 5 steps to analyze regional data and 1 step to do the analysis of the pathways. So in the first phase, we identify the system boundaries and what are the major key systems inside this region. Then we identify what is the major climate hazard. And then we build an impact chain model based on the hazards and the potential impacts. In this impact chain, there are a lot of variables that are relating with each other. And for these variables, we need to find their thresholds for the level of concern. And lastly, but not least, we identify a suitable pool of interventions which are able to address the main climate hazard in the region. So next, we proceed with the second phase, and we feed this regional data into the REPIA tool to quantify the emerging climate risk. The intervention characteristics are being fed into the DCRT tool, which is able to select and sequence the best climate adaptation interventions through an optimization process. Let's delve into the REPIA tool first, which essentially is an operationalization model of the well-known impact chain methodology. Here, we build a conceptual model of the region where we have variables of hazards, exposures of the region to these hazards, and the vulnerability of the region to these. These three components form potential impacts, like, for example, in the case of the region of Attica, socioeconomic droughts. And then we calculate the risk of this potential impact manifesting in the region using the well-known formula of risk, where risk is equal to hazards times vulnerability times exposure. These are the three components of risk, and for each component, we have different contributing factors, which are weighted in order to give an aggregate score of each component. However, each variable that contributes to a component, like, for example, hazard, is in a different scale, in different order than the other variables. So for this, we need to do some thresholding and some normalization. We allow users to normalize all the variables of the impact chain to a common scale of 0 to 10 using some defined thresholds. These are the thresholds for least concern about a variable, a medium risk about this variable, a high risk, and a critical risk. All values below the least concern level in a time series are given the value of 0. Any value above the critical risk threshold is given a value of 10, and everything between is scaled accordingly. We do this for both historical records and projections. We do this for historical records in order to validate that the thresholds we have attributed to the time series are well aligned with past observed events of, let's say, droughts or heat waves or whatever it is affecting our region. And for this, we seek data in past studies and repositories of historical data. For the projections, of course, we use available data from a repository like Copernicus, and we build the socioeconomic projections based on SSP narratives, or we find regional studies about this issue. So the user now uses the simple form of an Excel table in order to provide the relevant input for the impact chain model. You can see the variable names on one column, their weights, their types, and their thresholds. We can have multiple impacts in a region, so we produce multiple tables, and all of these are being fed into our Python application of REPIA in order to produce a result. The result looks like the graph you see on the screen now. So this is the socioeconomic drought potential impact and its risk based on the narratives of SSP1, SSP2, and SSP5 scenarios. Each curve stems from a single climate projection here, but we could have, for example, done an analysis of multiple projections with the same narrative and have an aggregate value for each curve. On the x-axis, you can see the time frame, and on the y-axis, you can see the risk value. So how do we use these curves now? This will be used as the input to the next model I'm going to show you, DCRT. So we can have a pathway being produced for each one of these scenarios. So the best pathway or pathways, for example, for SSP1 and SSP5, or we can aggregate these three curves into a single risk curve metric and then produce a single pathway that covers all three scenarios. Later, Sotiris will demonstrate to you the first approach when we build a single we build pathways for each scenario individually, because it's easier to understand. So let's go into the DCRT tool. The objective here is to identify the best pathway, so the best set of interventions in time. Of course, what is best changes according to various criteria, but the ideal condition is, of course, to minimize risk to the value of 0. Of course, this is impossible to do due to a large number of constraints, for example, costs, the acceptability, the social acceptance of solutions, the time frame of implementation, and various other things. And also, these things affect the effectiveness per se. So interventions that are within the pathway should have different characteristics that describe both the effect and other criteria. So in the dynamic contingency response tool, we have categorized 5 distinct sets of dimensions for which we provide characteristics for its potential intervention. Let's start with the first category, which is the effectiveness per se. Here we look at the regional scale of implementation for a specific intervention. For example, if we have sewer mining units in the region of Attica, if these are 20, if these are 70, or if these are 100. Then we look at what is their effect on specific vulnerability or exposure indicators of the impact chain. So if intervention X reduces vulnerability variable Y by the Z amount of percent. Then we have the cost dimension. Here we explore capital expenditure and amortization period and operational expenditure. The third dimension is feasibility. The attributes are technological readiness level, societal readiness level, and the ordering of interventions. For example, some interventions should be implemented in a specific order, or some interventions are mutually exclusive among them. The fourth dimension is the temporal. So we have considerations about lifetime, about sell-by date. For example, if intervention is no longer feasible or effective at a specific date in time. We have sell-by conditions. So interventions can be no longer effective if there are specific conditions in the future. And of course, we have the time to implement intervention, which affects the starting point of their counterbalancing the climate hazard. The last set is the externalities, and here we explore possible co-benefits of an intervention. For example, we have a nature-based solution that can provide ecosystem services, and we also explore some possible hidden risks. For example, if you build an intervention at a region, but there are not enough materials for its operation there. So again, we use the simple form of Excel tables for the user to provide their input. As you can see, in one column, we have the different interventions. And we also give, for example, here, the quantification of their effect on a specific vulnerability or exposure indicator. Other columns in this Excel table refer to lifetime or sell-by date conditions. Or, for example, in this part of the table, we have the precedence matrix where we denote the order of implementation. For example, a -2 value signifies that intervention I and J are mutually exclusive. Value 1 means that intervention I precedes J. A value of -1 means that I follows intervention J, and 0 means that these are not related. This is an important step because here we can evaluate the validity of a generated pathway. And of course, we can discard any sequences that are invalid. And this also is powerful because it can be used in order to describe some known strategies. So if we know in advance that the master plan in the region has this order of interventions, or if we have a strong preference for some interventions. So let's move into the optimization problem. Here we should look for a solution that specifically is a set of interventions, so let's say intervention A, B, and C, and their time of implementation. The challenge here is that we do not know in advance how many interventions will be considered in a specific pathway. So the input for the DCRT optimization is a vector that contains the timing of implementation for every intervention, and it would be 0 if intervention is not part of a pathway. We use a genetic algorithm to generate a population an initial population of solutions and then redefine them through the next generation and so on and so forth. And each generation is its sequence in the generation is checked for its validity. The invalid sequences are discarded, and then the valid sequences are being passed into the REPIA tool in order to recalculate the expected risk, expected climate risk in the region, and some other criteria. In this step, any sequences or any pathways that are below a user-specified performance threshold in terms of the risk reduction are discarded. And then when we let the algorithm run for 20 or 30 minutes, we end up with a population of solutions that includes Pareto optimal solutions. Why Pareto optimal? Because this is a multi-objective problem formulation. Specifically, the objectives that we use in the CRT are the following: the minimization of regional risk to the climate hazard, the minimization of the total cost of the pathway, the maximization of the technical and social feasibility, the minimization of deviations from annual budget, the maximization of co-benefits, and the minimization of hidden risks for the interventions. So we produce a lot of suitable Pareto optimal solutions that are non-dominated, and that means that each solution that is being produced is better than all the others in at least one of the criteria. And then we do a meta-analysis of results, for example, with user-specified weights, in order to explore the interesting pathways options. For example, you can set every weight to 0 and 1 to the weight of regional risk, and you can get the most performant pathway. Or you can, for example, check which is the pathway that has the least cost. But how does the results look like? This is an indicative outcome, and Sotiris later will explain you the whole process implemented in the region of Attica. And in this graph, you can see with the red line, the baseline regional risk as it has been produced by the REPIA tool. The blue line now is the risk after implementing a specific pathway, the specific solution that you see on the screen that has 6 interventions. You can see the names and their specific decision points. So now we are at the process of culminating everything that you just saw into a single web service that will be a decision support tool. We have discarded the 2 difficult names, the CRT and the REPIA, and we opted for the new name Paths. And this is just a sneak peek of its initial web page, and the tool will be released next month, so stay tuned. Now, before going into the second part of the presentation, where Sotiris will focus on our case study, I again invite you to answer 2 more questions about this phase of the presentation. So the first question is, if you think that what you just saw as tools before showing you the interesting results can be useful in order to address climate risk in your specific region. Let's leave around sometimes it takes some time to reload. I see in the chat some concerns about Mentimeter. I will go back a little forth. So yeah, it is just slow to reload. Okay, let's go to the second question. Okay, so people have already answered, have already some 8 responses, I think. So the second question here is, who do you think can benefit from such decision support tools in your specific region. Lots of interesting responses here. Majority chose policymakers. It's constantly, this figure is constantly evolving. Yeah, I think we got many responses already. You can always have the opportunity to continue voting or going back to the previous questions later or in the third phase of the questions. And now I want to give the floor to my beloved colleague Sotiris to present you the East Attica case study and the results we had there. Please, Sotiris, the floor is yours.
So hello from me as well. This is the impact chain that we used for East Attica. So we have the different hazard elements that you can see here. Essentially, those are climatic hazards. We have rainfall, temperature, the standardized precipitation and evapotranspiration index, or LSPA. This is an index very commonly used for studies related to droughts. We use the average temperature in the summer months, which is the typically hotter period in Greece, and the number of days with temperature over 30 degrees. With respect to exposure, we took into account the population, the industrial activities, and the agriculture that are present in the area. And regarding vulnerability, we used 4 elements. The first of them is the potential inadequacy of the central water supply system to cover the increasing demands. I have to note here that this central system is a very large, the largest water supply system in Greece, and it covers essentially the entire Attica region, not just East Attica. And then we have the dependency of irrigation demand on groundwater as a vulnerability element. We have the dependency of domestic and municipal water demands on the central supply system. And last but not least, the dependency of the industrial demands on the central supply system and groundwater. So in this case, we know that some water from groundwater extractions is also used for industry. In the end, we assess the impacts from the point of view of socioeconomic droughts, which is basically the situation where the demand for water surpasses the supply. You have seen this figure before. It's essentially the baseline socioeconomic drought risk values for SSP1, SSP2, and SSP5. And by baseline, we mean that no interventions have been implemented yet. So this is the risk values that the REPIA tool gives us without implementing any interventions. As you can see, the SSP5 scenario is the most extreme one, while SSP1 and SSP2 resemble each other quite substantially. The simulation takes place from 2021 until 2100. Regarding the assessed interventions, we have considered sewer mining, rainwater harvesting, controlled environment agriculture, the treatment and reuse of wastewater treatment plant effluents, seawater desalination, and of course, information campaigns and policy-related measures such as pricing policies and so on. And in these figures, you can see how each of those interventions affects one or more elements of vulnerability. For example, rainwater harvesting can reduce the dependency of domestic demand on the central water supply system, and at the same time, this way create some spare capacity for the central supply system to actually support other elements. Control environment agriculture, on the other hand, and the reuse of wastewater treatment plant effluents reduce the dependence of irrigation demands on groundwater. So each one of these interventions is linked to some vulnerability elements. And then we had to assess several points regarding those interventions. For example, the cost. We viewed the cost, or we faced the cost from the point of view of Greek regional authorities. To give an example, the capital expenditure for reclaiming and reusing wastewater will be covered by at least 90% from the European Union. So in our case, we only took into account the 10% that the Greek authorities will have to cover. The efficiency of the interventions, on the other hand, so what is the impact they can have in these vulnerability elements, this was assessed based on previous studies in literature or also modeling. For example, in the case of rainwater harvesting, we set up a model to see the impact of rainwater harvesting, how much water we can collect for a certain house in East Attica. Finally, the extent of the application of these interventions, so how many rainwater harvesting systems we will have, for example, this was based on simple assumptions, so we did not carry a detailed analysis. Those are the results for East Attica for SSP5. As we saw before, SSP5 is the most extreme socioeconomic scenario, and climatic, of course. Almost 180 solutions were derived from the methodology, and in this part of the slide, you can see the Pareto front comprising of the total cost of each one of the derived pathways and the integral of the remaining risk. In other words, when the remaining risk is low, we have a high risk reduction. And on the y-axis, we can see the solutions that have a large cost. As you can see here, there is a small break, a mild break in the slopes in this graph. Let's call it the elbow point here. To the left of which we see that the reduction of 1 unit of risk is more expensive, essentially. So from this point to the left, each reduction of risk becomes more expensive. Now, in this table, you can see for each intervention, the selection probability between all these solutions and what was the average year of selection by the algorithm. For example, campaigns and policy was always selected, and as a matter of fact, it was on average the first intervention that the methodology selected. Then we have the two phases of reclaiming wastewater and reusing it. We applied this measure in two phases because the regional authorities also plan to implement this measure in two phases. So we see that both phases were always selected, and immediately after the campaigns and policy, we have the sewer mining, the control environment agriculture, and rainwater harvesting, and in the end, desalination, which, as we can see here, was almost always selected, but the average year of selection was quite late. The reason for that is that desalination has a relatively high operational cost, so the algorithm often tried to select it as late as possible. So we see that we have some measures that were almost always selected and some that were not. An example is rainwater harvesting. We have this measure applied in two stages, one for 15,000 houses and one for 5,000 houses in East Attica, and we see that it was selected at maximum, so second phase of 5,000 houses at 37% of the times. A reason for that is that we assumed this measure to be quite ineffective for dry years, so 3 years with small spay values. Now, out of those Pareto pathways, we analyzed further 4 of them. The first one is the pathway with the largest risk reduction. The second one, so pathway 2, is the one with the least cost. Pathway 3 is one that aims at balancing the risk reduction and the cost, and essentially it is the elbow point in the Pareto front that we saw in the previous slide. And pathway 4 accounts for all criteria with equal weights. Now you can see here the adaptation pathways, so how each solution was selected in time versus the risk in the y-axis for pathway 1, so the largest risk reduction, and pathway 2 the least cost pathway. And as you can see, the red line, which is the baseline risk, is reduced much more in the largest risk reduction pathway, pathway 1, compared to the least reduction pathway. So we have a large difference in case of risk reduction, and of course, a difference in costs as well. If we look at things a bit more closely, in this table here, we can see the different interventions and the implementation here for each one of the 4 pathways we described above. And we can see that pathway 1, the most effective one, adopted a rather aggressive approach, implementing desalination and wastewater reuse quite early. So those were the first 2 measures that were implemented. Nevertheless, those have quite a high OPEX, operational cost and capital cost. While pathway 2, the least cost pathway, delayed the wastewater reuse. So we can see it was only applied after 2037 and completely omitted desalination to save costs. Now, the balanced pathway, the elbow point pathway that we discussed before, gave priority to wastewater reuse, campaigns and policy, and still opted for desalination, but delayed it substantially compared to pathway 1 to save some costs. So this is more or less the logic behind the algorithm and the selection of the measures. Here we can see the results for SSP2. As we saw before, SSP2 was very similar to SSP1, so the results were also similar, and the risk was much smaller than SSP5 that we saw before. Now the results were largely similar to SSP5. We saw again that information campaigns and policy measures, the reuse of wastewater, desalination and sewer mining were amongst the measures most frequently selected, while rainwater harvesting was the one less frequently selected. Some remarks about the methodology. First of all, the methodology and the results were discussed in detail with stakeholders, and more specifically, the Athens Water Supply and Sewerage Company, thus validating the approach. Within the IMPETUS project, there is a second case study, the Zemgale region in Latvia, that will follow the same approach. And with respect to the next steps, as you probably realized, the approach currently is based on the impact chain. And while the impact chain is a flexible and easy to use approach, thus allowing the methodology to be applicable in several case studies and environments, different climatic conditions, there is a way to largely improve the results by using, instead of the impact chain, hydraulic, hydrological, and water management models. So in the next step, we will replace the impact chain with tailored models in the frame of another project, namely Recreate, where we will transfer everything that we saw here for East Attica region in the frame of IMPETUS, and we will try to make the analysis or else the links between the climatic hazards and the impacts more robust. And that brings us to another question. So do you think that a regional authority will find it easy to apply the adaptation pathways of the regional decision support tools, the pathways that we just presented? I think that maybe we can give some more time and then proceed. maybe we can already proceed to the next one.
Yes, I think if you move, it will reload. Yeah, just reload.
Okay, okay.
Okay, you can. I think you can move to the next part.
Yes, I'm trying, but it seems it has. I don't know if Raul can help me move this slide. Move to the next slide.
Yeah, I'm trying, but for some reason it's also not working.
Yeah, it seems that the Mentimeter got stuck in this.
Yeah.
In this
Okay.
slide. But I think people are able to go to the next one and vote, but we just can't see it.
Yeah, I think we can maybe just proceed
Okay.
with
In the meantime, I can answer some questions in the chat.
Yeah.
Yeah, let's check. Okay, so we have one question about we have two questions about the paths tool. So the first one is if the developed tool will have historical data up to 2024, and then do the projections will be from this year on. Oh yeah, that's an interesting question. Well, the paths tool does not contain any data itself. The user of the paths tool will supply the data in order to run the analysis. The historical data will be used in the previous step, so where we are trying to examine the system and see, for example, what were past records of a similar, let's say, flood or drought or heat wave or something that affected the region. And paths, in paths, the user supplies as input the projections with the weights and thresholds for the variables that form the impact chain, and also the user supplies the information of the suitable, the characteristics, let's say, of the suitable interventions. And paths runs both the REPIA tool in order to generate the future risk projection, and also runs the DCRT tool in order to generate the best solutions. So this is how it will work. Always the first step will be a desk study of the user in order to gain insights on the region and the problems that it has. And for the second question, of course, yeah, we will have a manual as a deliverable specifically of IMPETUS, a manual of the paths tool and how all these algorithms work and what do you need in terms of desk study to identify, for example, the climate hazards, thresholds for variables. Everything will be well documented in about 1 month. And we would like to see also some feedback later if any of you is interested and can access paths and just send us an email about, oh, hi, I saw your webinar and then logged into paths and have some comments. We'll be very glad if you do so. Have any other question? I think what Elisa is asking is also a nice point of discussion if you have the time now. Well, yes, I can try to provide an insight from our experience. So at least 3 out of, let's say, 5 or 6 of the interventions provided by each solution that we saw in our case are actively being designed or tested in the region. So, for example, the regional authorities are already designing wastewater treatment plants that have tertiary treatment, and the algorithm actually selected the time of implementation pretty close to where these are already projected to be in operation, so within a time frame of plus or minus 5 years. So this was a success of the algorithm. And also, the other intervention that was frequently suggested by the algorithm, the desalination solution, is also one of the plans. But there is a peculiarity in our case. The focus is not so much on local adaptation solutions, but solving the problem at a much greater scale. So while the pathways generated from the tools are very realistic, and these are options that they will use, the majority of the let's say risk will be reduced by some other interventions that we haven't included in the pool. So in terms of local adaptation, yes, the regional authorities are already thinking of these interventions and pretty much in the sequence that the tool suggests, but there would be also some additional more larger scale works that will supply water to the system. Also, within the feedback we got from our stakeholders, they also provided some insights about other features that they would like to see, for example, specifically in water systems, let's say, or some things that we would like to see in the impact chain and other updates. In the view of our regional authorities, such tools are very useful, and they can also help having a very high level of knowledge about whether something is useful to be evaluated in a study or not. Let's see if we have another question in the chat. Okay, so another question is how your tools take into account conflictual strategies from different water resources and users. What is the impact of proposed solutions on CO2 emissions? Well, for the first part, we take into account the different aspects of variables contributing to exposure or vulnerabilities. For example, we try to keep a balance. The tool tries to keep a balance between interventions that give water for agriculture, or for industry, or for domestic water demand. The way this is taken into account is that if, for example, you reduce only one of these components and not the others, the weighted effect of this component of risk will not be lowered significantly. So you need to balance your selection of interventions in order to keep things running smoothly. So conflicts about interest between various end users are being accounted here. The second part is the impact of proposed solutions on CO2 emissions. This is somewhat explored with different tools that we have built within IMPETUS, and these are tools that provide input to the DCRT. So, for example, what we are describing here is some solutions that can have, for example, high CO2 emissions. This is regarded as a high risk, as a hidden risk, sorry. And let's go back some slides. I don't have control, so Raul, please, can you go back some slides?
Just let me know when to stop.
Yeah, go. Stop here. Go a little bit forward. A little bit forward more. Sorry, it was delayed on my screen. I just saw the view. So, back. here. As you can see, one of the criteria in the optimization is hidden risks. And hidden risks are being calculated on the basis of various KPIs from a tool that is called the ESCI factor registry. We didn't present it today. So one of the KPIs there is about the environmental friendliness, let's say, of an intervention. And if a proposed pathway, so a proposed solution has high emissions, maybe it is performant on some of the other criteria, but gets lower score on hidden risks. So we can explore solutions that are good performing, but they are not very good for the environment or for emissions, or vice versa. We can account for this. Let's see in the chat if you have any other question. Yes, we will define the manual, what are the necessary data, at least from the perspective of a water system, but because both of our case studies are about water systems. We have the East Attica region, which is focusing on droughts, and we have another region where we study now, the Semgala region in Latvia, which is focused on floods. So at least for water systems, we will have in the manual defined some key data that we should look into. Okay, and we have another question about if the PAFS tool will be available in different languages. Currently, it will be in English, but this is a customizable tool. It's based on the platform we have used before, and there we had Greek and English. So I don't see any reason why will be not possible, but of course, everything needs some budget and some time. But if there is enough interest, for example, I don't know, in Germany, as I think Daniel is asking the question, yeah. If there is enough interest in Germany, we can of course produce a version of the tool that is tailored to the region and includes a different version of the REPIE tool that is more, let's say, tailored to an energy system or a water system or what is relevant for the case study. Okay. Let's see if we have another question. No, for the time being, we do not have anything else. Let's wait 2 minutes if someone else wants to write a question. In the meantime, I would like to point out that the work you saw today is not the outcome of just 2 people working here, me and Sodiris. It's the outcome of many people from our team working on this. And of course, many partners within IMPETUS have worked with us, have contributed to us either directly with working on some of the tools that are the precedents to what you saw today, or giving us feedback, or helping us with the methodology, or being the I don't know, the test subjects of us implementing the tools. So you can see here on the screen every organization that has contributed specifically to these things that you saw. And this is the whole IMPETUS consortium, and I want to thank all of our colleagues for this. Please stay tuned. We'll release PAFs. We'll be very glad to hear your opinions when this will be released as an alpha version, and it will be online. And who knows, if you want to collaborate with us in a future study, please drop us an email. Thank you very much.
Thank you all. Looking at the time, with just a minute before it's 3 o'clock, I'd like to thank both Dionysius and Soterios for their presentations, and also thank you to the participants and those who stayed till the very end of the webinar. So thank you very much, and enjoy the rest of the day.